We're going to talk about the parametrization of plane curves, and this is really an introduction to this topic. So just high level, what does this mean? So typically when you think of an equation, like you could think of something like y equals 3x minus 2. So typically this is how we think of equations. But with parametric equations, what's going to happen is you instead are going to have a formula for your x and then another formula for your y. So in the simplest form, I could say that x equals t and y equals 3t minus 2. But honestly, you can do whatever you want. So you could do weirder things like x equals sine pi t over 4 and cosine equals 3t over 2. You can make whatever formula you want for your x and y. So first things first, let's discuss some vocabulary since this is a newer topic. So we're talking about parametric equations, so just how do we refer to these things? So I have a whole list of things I just want to kind of discuss so you get the idea of how we describe this. So if we describe x equals f of t and y equals g of t, so kind of like what I was showing you before. So if we describe this over some interval I of t values, then we say that these equations describe a parametric curve. So taking these two things together, they're going to make their own graph, and we call that graph the parametric curve. And then the equations x equals f of t and y equals g of t, these, by each of these on their own, are what we call parametric equations. So parametric equations create a parametric curve. And then a coordinate, so now instead of having x, y as your coordinate, we can alternatively think of this as f of t and g of t. So this would be how we would describe a coordinate. And then t itself, we call t the parameter. So we have different ways to describe coordinates, and t is the parameter. And then we have the interval I that our parametric curve runs through. This is called our parameter interval. And then if I is a closed interval, i.e., so if t is between a and b, then f of a, g of a, we call that our initial point. And f of b, g of b, that's our terminal point in the interval, if it's a closed interval. When a curve is described with parametric equations, we say that we have parametrized the curve. And finally, another way to describe parametric equations with an interval is to call these the parametrization of the curve. So if we think back to kind of what we were talking about, so if I start with this equation here, y equals 3x minus 2, I could just call this y equals 3x minus 2. But if I wanted to parametrize the curve, then I could redescribe it like you see here. So any curve can really be parametrized, and so that's just something that we're kind of thinking about. Okay, so first things first, let's just kind of get used to like what happens with how these are graphed, okay? So we're going to sketch two curves here. So I'm going to have the first one, x equals cosine pi t over 4 and y equals t. T will be between 0 and 8. And then the second one will be x equals t squared, y equals t minus 2, and t will be between negative infinity and positive infinity. Okay, so let's start with x equals cosine pi t over 4 and y equals t. So t is between 0 and 8. Well, if I just think about how you would try to graph this. Like if you think about this, right, you can see now that there's three pieces of information that you need, right? You need your input is the t, and now you have two outputs, x and y. And so we can make a table of values just like we would back in the good old days of algebra. And I can just have a table now of t, x, and y. And so then it's just kind of choosing a few values of t, enough that would get you the idea of the curve. So in this case, I'm going to have 0, 1, 2, 3, 4 just to establish the pattern. And then I'll do a couple more just to round out the interval. So I'll have 4, 6, and 8 at the end here. So I've got my t's, and so then this really is just as straightforward as just plugging them into each individual formula. So if I plug in each one of these t's, so I get the values that you see here. So for instance, when t is 0, I'll have cosine of 0 is 1, and my y is equal to 0. When t is 1, this becomes cosine of pi over 4, so that's square root of 2 over 2, and this will be 1. And so on and so forth, right? So you can just go through and compute a handful of these. And so I think if I just left you to your own devices, like this is kind of an intuitive thing. It's weird because there's a t in it. But as far as like if you had to figure out how to get this done, I think a lot of people would probably just start inputting in t's. And then you still graph on your X and Y just coordinate space. So I've set this up so that I have positive and negative X values, right? Because I can see I have positive, negative X values here. And then I have my Y's going just positive from 0 to 8. So you just now want to draw your Cartesian coordinate system based on whatever you found for your X and your Y's. But then as far as like, how do I actually graph this? So each one of these XYs, now it's just like a normal graph. And so you just graph the pair. You don't have to worry about the T. So you can just go ahead and plot your points. And then from here, you can go ahead and you can connect them. So I can see now that, and like the other thing is you do want to now go in the order of your T's, okay? So as I'm connecting these, so I'm not going to go from here to here to here. So what I mean is I started here, here was where my T equals 0, this was T equals 1. So the one thing with this is that you draw your graph in the order of your T's. So this would be in the order of my T's. And now I can see if I wanted to say continue this, so I know that this only goes up to 8, but if this were to go up further, it would just kind of continue up like this. Okay, so this is kind of this wavy spiral pattern, okay? Now, the only other thing is if you want to include the T's, sometimes that information is helpful. And so you can like label your different points just to describe kind of the movement here. So you would describe those points individually. This is where T equals 0, this is where T equals 1, so on and so forth. And so that does tell another story, right? This does kind of tell you now the story of like how the order of the parametrization went. So this is the extra piece of information that you can include if you feel like you need that. And by the way, if you are getting thrown off, like if you aren't sure how to graph this, then I would include just the order of the T's, because then that's going to be, it's almost like, you know, connecting the dots in a certain order at that point. So if you get confused when you're trying to graph these, you can always include that information about the T's. Okay, so let's do the other graph now. So in this case, so my T's go from negative infinity to infinity. So in this case, I'm trying to just establish this like long-term pattern. And it's going to be the same idea. So I set up a little table here. So I have different values of T's. And so what I'm going to suggest actually is for you now to pause the video and for you just to fill this whole thing out and for you to graph it, just to get some experience with it, and then hit play when you're ready. So, okay, I have different values of T's here. So I go ahead and I plug those in. So first things first, I would just double check that the value on your table matches the value on my table. And from here, I can set up my axes. So I need only positive X's and negative Y's. So I set up an axis to reflect that. And then I can go ahead and plot my points. And so now from here, I can go ahead and connect everything. And again, if you're getting kind of thrown off, you can go in order, right? So if I wanted to, I could say this is T equals -4, T equals -1, T equals 0. And so this is the order that I connect everything in. And so again, that can be the other missing piece if that's throwing you off. Okay, so that is how you graph. It's a little cumbersome. And as we can see now, like this is basically just a sideways parabola. So in some ways, parametrization, it can sometimes hide like what is the shape that we're trying to come up with. And so there's going to be this natural question of, okay, well, is there some way for me to take these two equations and then put it back into, say, like a normal XY equation? And so that's going to be the next thing that we're going to talk about. So this problem is, there's a lot kind of going on in here. So it says the position P of xy of a particle moving in the xy plane is given by x equals 2t minus 5, y equals 2t, and t is between 0 and 1. So we want to identify the Cartesian equation for its path and graph the equation and indicate the portion of the graph traced by the particle and the direction of motion. Okay, so there's a couple different ways on how you can approach this. I think it kind of depends on the question, I guess. But to me, I like to first set up a table. And I don't need all the t values in this case. I just need enough information to know where I'm going to start and stop in this case. So I'm just going to set up 0, and 1. So if I plug in 0, I get negative 5 and 0. And if I plug in 1, I get negative 3 and 2. So this is going to help me identify my start and stop on this graph and also this direction of motion. Now, if you feel like you need more points, that's totally fine. But in this particular example, I know how this is also going to work out, so I know I'm going to be fine with 2 points. So let's talk about how do I get this now into a Cartesian equation. So I have x equals 2t minus 5, and then I have y equals 2t. So you can be a little creative now in how you are going to relate these two equations. So basically what you're trying to do is you are trying to bring the t together in these two equations so that you end up with one equation in terms of just x and y. Now, to me, the thing that I notice, this is 2t, this is 2t. So I could totally just replace my 2t with y to rewrite this as x equals y minus 5, and then I get y equals x plus 5. Now, you can also go a longer route and you can say, oh, t, let's see, I'll just shove this in the corner here, t equals y over 2. And so you could take a lot longer route then and say, okay, well, I could easily solve for t, so now I can shove it into this equation here. And if I did that, this would become x equals 2. So now where I have a t, I'll replace it with y over 2 minus 5. And so that's going to give me that x equals y minus 5. And that gets me back to the same equation. So in terms of like figuring out what Cartesian equation are you talking about here, you have a little bit of a license to be creative. It's however you can boil down the t's so that you're left with an equation that just has x and y that you can all easily then solve for y. So in this case, this is a more straightforward example. Sometimes this takes a little more finessing, and we'll see another example of that in a moment. Okay, so anyways, so at the end of the day, the Cartesian equation in terms of just x and y is going to be y equals x plus 5. So now I've got my start and stop. I've got my Cartesian equation, so we can go ahead and graph this. So I'll make a little space. And so the 2 points that I want to make sure that I have are the ones here. So negative 5, 0, and negative 3, 2. So let's see, I'll draw here 1, 2, 3, 4, 5, and then 1, 2. So I've got negative 5, 0, and I've got negative 3, 2. So here is my line in this case. And then we're supposed to indicate the direction of motion. So this is the other reason why it's kind of nice to have this table here, because now I can see, remember, this is my t equals 0 and this is my t equals 1. So with a parametrized curve, if you want to just indicate the direction or the order that the t's are going in, you can put little arrows on, and then that indicates that. So I don't have to write the t equals 0 and t equals 1 unless that's helpful for you, but the arrows will indicate that direction of motion. And now we have everything that this particular question is asking for. So now let's contrast that to another example. So I've got x equals t over t minus 1 and y equals t minus 2 over t plus 1. Okay, and in this case, I need this to go from negative 1 to 1. So in this case, I can go ahead and I can do the same thing. So I think I'll start there. And again, I just kind of want to know what's going on with a couple of these points. So let's see, I'll have t, x, and y. So this is going to be negative 1, 0, and 1. I'll start with those. So if I plug in negative 1, I'm going to get negative 1/2. And then let's see, for the other one, I'll get a problem, right? So this one is actually not applicable. And so you may have thought to yourself, oh, well, it's weird that I have this, the endpoints are not included. And if you think about it now, okay, this is why they're not included. And so if I do the same thing for 1, right, I'll see I get the same thing. This is not applicable, and I only can get a y coordinate. And so if the point is not applicable, then the whole point does not work, okay? So that's something that you'll encounter as you're kind of going through these. And so then, of course, what are we going to have to do? We're just going to have to recalibrate. So, okay, no problem. We can totally do that. So I just have to choose some different values that are more useful in this case. So I can use -1/2. And at -1/2, that will give me +1/3. And then if I plug in -1/2 into my y, I get -5. If I plug 0 into these, so this will be 0, and then let's see, this will be -2. And then if I plug in 1/2, I'll get -1 and -1. So I have still a lot of other information that I need, but I'm going to hope that this will be enough to kind of get me started. And now for the tough part of getting that Artesian equation, or Cartesian equation. Okay, so in this case, let's make a little space. So now we have to think of how am I going to relate one equation to another. And so I think where I'll start is I am going to try to solve for t in this equation here. So what I can do is I can multiply both sides by t minus 1. So I have x times t minus 1 will equal t. And so I'm trying to solve this for t. So what I'm going to do is I'm going to distribute. So this becomes xt minus x equals t. I bring the t terms over to the same side. So now I've got -x equals t minus xt. And then I can factor out the t. So I'll take out the t. So this is 1 minus x. And so what I'll get here is, so my t equals -x over 1 minus x. Now, I can take this negative on top. I'd rather not have this be negative. So what I can do is I can take this negative and multiply it into the denominator. And what that will do is that will reverse the order of my denominator. So if I take this negative and put it here, negative times -x is +x, and a negative times 1 will be -1. And just in case you're having a moment of like, wait, why can you do that? So sometimes people forget this. So if I have -a over b, that is literally the same thing mathematically as a over -b, and that's the same thing as just having a negative in the middle of your fraction. So you're always allowed to take a negative and move it, and so in this case, I just don't want to have that extra negative here, so I'm just going to shove it into the bottom and reverse the order. Okay, so that being said, let's make some space. So I've now got my t is x over x minus 1, so now let's take that and put it into here. So this is going to be y equals x over x minus 1 minus 2, and then x over x minus 1 plus 1. So I need to turn this into something that is actually usable, so I'm going to multiply the top and bottom both by the same thing, x minus 1. Okay, so in doing that, this first fraction, so x over x minus 1 times itself will just leave me with x. And then this will be minus 2 times x minus 1, so I'll deal with that in a moment. And then this other one becomes x plus 1 times x minus 1. So let's see, if I sort everything out, I get x minus 2x plus 2 and x plus x minus 1. So ultimately, I get that my y is going to be equal to 2 minus x over 2x minus 1. So there's my Cartesian coordinate. So, or my Cartesian equation. So as you can see, sometimes this can be a lot of work to figure out your Cartesian equation. So now I have to figure out, this is a rational expression, right? So I now have to figure out how to put this all together in a graph. So if I come back to that original information that I had, so this is talking about positive values of x but negative values of y. So let's see, I will draw my axes. So here's 1, here's -1. So we have 1, 2, 3, 4, 5. So I have 1/3 and -5, so I'm somewhere down here. And then 0, -2, so that's somewhere here. and then -1, -1. So now I can see kind of how this rational curve is coming together. And so I know that for any rational function like we have here, so there are asymptotes with it, right? And so the asymptote in this case, so the asymptote's going to be this equals 0, so 2x minus 1. This equals 0 when x equals 1/2. So I know that there's actually like this little asymptote right here, right? So I can now get a much better picture of kind of what's going on. And then also I know there will be a horizontal asymptote at -1/2. So I can tell if I take the limit as x goes to -infinity, you can figure that out. If you don't remember where the asymptotes come from, that's not really something that's going to make or break you. I do have some videos on that if you want to review it, but it's fine for our purposes. So I get something that looks like this. And so what I can see now is, so the reason why -1 and 1 were not included is that that's actually where these asymptotes are going to lie. And so I've just got this branch of the function here. And so it can definitely take a little bit of work to piece together all the parts of like why are you given the certain t's that you are. But once you start graphing everything, you should be able to make out the general shape of the graph. And I would assume that, you know, ideally in calculus, you at least remember this has kind of this type of curve with asymptotes in it. And so then you can kind of finagle it from there. Okay, so there are two examples of that. I do want to just talk about how can any function be parametrized. So we can literally parameterize any curve. So if I have the curve y equals f of x, so any curve that I have, I could always just let my x equal t and then my y equal f of t, and then boom, you've got a parameterization. So any curve can actually be parametrized. And then if we want to find a parameterization, so let's just do one more general kind of equation here. So what if I wanted to find a parameterization for the line through y equals ab with slope m? So you can use this idea here and just find your equation of a line, but I'm going to show you another way of how you can parameterize, because you can really parameterize any way that you want. So I'll just show you kind of a more creative way of how we can approach this. So remember that for any line, we have the point slope form y minus y1 equals m times x minus x1. So that's just your general equation for any line. So if I plug in the information that I've been given, so I'm going to plug in my y1 will be b and my x1 will now be a. So there's kind of my situation for this line. And so, like I said, I can parameterize any way that I want. So what I'm going to do is I'm going to let my t equal this x minus a. So let's make a little more space. So if I let my t be this x minus a, then what I can also say about setting up this relationship is that x is going to be equal to t plus a. So what I'm going to do is I'm going to replace this new relationship for x. I'm going to replace it with this t plus a relationship. And so if I plug that in, so look what I get. Now I have this t plus a minus a. So the a's obviously drop out. And so the whole right side of my equation becomes y minus b equals mt. And now the parameterization for y reveals itself. This just becomes y equals mt plus b. So you could just say that your x would just equal a, but you'd get a more complicated equation. So in this parameterization, this is a little bit of a cleaner way to parameterize stuff. So my x will equal t plus a, and my y will equal mt plus b. And now my t can stand for any values that we want. So this is another way that you can parameterize things. It's just something to kind of think about. And that's where I'm going to leave it. I'll talk to you guys in another video. Bye!